Okay, let's see. I forgot to have it on the record. There we go. Okay, so we are recording and off we go. New topic for today. Real quick though, I just want to touch base about the exam. So I sent the email out last night. Again, apologies for the delays in getting that graded. The technical impediments were unprecedented in my experience. Never had to deal with anything like that. And by the way, we're still not fully recovered. Anyway, sorry that slowed us down. Glad we finally got it done. And again, the test was hard, right? It was a hard test, and the curve correspondingly, right? So I think grades turned out very reasonably, and overall for the class as a whole. And anyway, all right. Okay, moving along. So new topic. I'm going to talk about Stokes' theorem. So this is another one of these theorems that you can kind of see it coming. Just without even looking at the details, we're going to talk about boundary. We're going to find an accumulating quantity. We're going to, as a result, interpret that it behaves like stuff. We're going to come up with a associated notion of density, and then we're going to put it all together and have a theorem. The pattern is overwhelming, and again, I like to develop all of these theorems in this sort of patterned way to emphasize how that's all really the same, deep down, the same sort of basic fundamental ideas. And I think there's a lot of opportunity for intuition based on that. Right? If you know that Green's theorem and the divergence theorem are very closely related structurally, then what you understand about Green's theorem can be your guide to helping you understand better about Gauss's divergence theorem. Right? So analogies are wonderful opportunities to capitalize on. Somehow these lights came on. Hang on a second. That's better. Okay. All right. So, some details. Let's talk about boundaries. Remember, as with several other theorems we've discussed, boundaries are now oriented things. And we've got to pay attention to how boundary orientations are created. Again, it's a standard. Now, it's an arbitrary standard, but it is a standard. And by the way, this arbitrary standard is closely connected to other arbitrary standards we have written down or will write down. And so it's highly non-negotiable, right? So yes, it's arbitrary, but we have to do it this way. Okay, so the big idea, if you have an oriented surface, right? And keep in mind, oriented means that it has an orientation vector. And for a surface, an orientation is represented by a normal vector indicating which direction through the surface is to be considered the positive direction through the surface. Okay, so there's my oriented surface. Surfaces have boundaries. The boundary here is a curve. The boundary, of course, is sort of the edge of the surface. It's as I like to say it, where the ant would get confused if there was an ant walking around, right? And so just for fun, let's point out, if this is an ant, and if the ant is kind of walking around, everything kind of looks normal, and he thinks nothing of it until he gets to here, and then he has questions. Wait, oh my God, what happened to the surface? Where did it go? There's no surface here. I've reached the edge of the world, right? Very confused ant. That's where the boundary is. There we go. Okay, so that boundary is a curve, and we have the question before us, which is, on that curve, which direction are we going to call the positive direction along the curve? How is that curve to be oriented? And we have a rule that helps us answer this question. Again, arbitrary, again, standard. The big idea is, and let's see here, let me try to clean up the mess I have here. The big idea is you take your surface wrong color. You take your surface orientation at some point on the surface, not on the boundary, on the surface. Okay. Then you define a swirl. The big idea of a swirl is it is a choice of some direction around that normal vector. And of course, there's two ways that you can kind of rotate around that normal vector, this way or that way. And there's various terminologies that you could throw at this. You could try to talk about clockwise, counterclockwise. That's actually not going to work very well. Can't describe. You see what I've got drawn there? If I were to call that counterclockwise, that probably wouldn't bring up too many objections. But let me point out, if you look at my finger now, as I wave my finger around in the air like this, from your point of view, it looks like my finger is going around counterclockwise. But from my point of view, it looks clockwise. Right? So clockwise and counterclockwise is a troubled concept in 3 dimensions. Doesn't really work super well. Now you may be having flashbacks back to chapter 1, where we talked about clockwise, counterclockwise, and then we bumped it up to 3 dimensions, and the answer was that we had to talk about right-hand stuff, right? We made up this idea of right-hand order, and that connects with determinants and blah, blah, blah. So we're basically going to use the right hand again, and the rule, as I have circled there, is you point your thumb of your right hand in the direction of the surface orientation, that unit normal vector, the orientation unit normal. The fingers of your right hand, bending the way fingers want to bend, point in the direction of the swirl. Right, so that's how we identify that swirl. And once you have the swirl, then it's just a matter of keeping track of, but how does that, when that sort of side swipes up against this boundary curve, here's that boundary curve again, and as it kind of brushes up against the boundary curve as it swirls around, that's going to point in a well-defined direction around the boundary. And there you go. That is our boundary orientation. There's different ways to define this. I think this is the easiest one, all things considered. Okay. Questions? Is everybody happy? Okay. Alrighty, so that's how boundaries work. Do keep in mind, very important, henceforth, boundaries are oriented. You just got to make sure you remember that. Okay, so that said, we're going to blow through some of this stuff here because it's all the same as stuff we've seen before. I'm going to say boundary circulation accumulates. You've heard me talk about that in the past when we were doing Green's theorem. In Green's theorem, we had a 2-dimensional region in a 2-dimensional plane. Here we have a 2-dimensional surface, still 2-dimensional. It's in a 3-dimensional space, but it's still a 2-dimensional thing. It still has boundaries that are curves. It's a lot like what we were studying when we were doing Green's theorem. And when we were doing Green's theorem, we found boundary circulation accumulates. And unsurprisingly, given how analogous these things are, same deal for surfaces. And the picture is morally equivalent. Given this surface, oriented as indicated here. All right, and you play the right hand, thumb in the direction of the normal, you look at the fingers and the swirl, and that's going to set up an orientation on the boundary that goes like so. And then you look at the other side, you look at this, oriented as indicated, and again with the thumb and the fingers and the swirl and the blah blah, and that's going to give a boundary orientation oriented like this. And again, the only thing that is in question as to whether, is the whole, the sum of the parts, is this cut edge here. And again, that cut edge, just like with Green's theorem, same story. Just like with Green's theorem, that shared edge appears twice in the sum of the parts It appears twice but with opposite orientations, therefore they have opposite values and therefore they cancel. Just like with Green's theorem. The analogy is overwhelming, right? And I think this is an excellent opportunity. So, strongly advised suggestion here. Look back at the exact argument that we made with Green's theorem and notice how it's morally equivalent. Same basic idea, not that little bit different. Geometrically, it's a different context. We're in 3 dimensions instead of 2 dimensions. Of course, it's a little different, right? But aside from context differences, it's morally the same idea. Okay. Everybody okay with that? Questions? Okay. Well, isn't this awesome? We have an accumulating quantity. We also know from chapter 6, whenever you have an accumulating quantity, we have a strategy that's highly successful in context over context, which is you have an accumulating quantity. You can use that to interpret that as a kind of a stuff, that stuff is distributed over the interior, and that there's an associated density. And, no change here. Now, look through these details at your leisure, if you're so inclined, if you want a little clarification. The punchline, though, is, as we just said, circulation behaves like stuff. Of course it does. It's an accumulating quantity. All accumulating quantities behave like stuff in a way. And because it's a stuff, we have an associated notion of density. Now, let's be careful how we write this down. We're going to talk about circulation density. Circulation density. Let's be precise about what that is. Circulation density means circulation boundary. Circulation, of course. Circulation per unit area. That's what density means, right? Stuff per unit size. Here the stuff is circulation. Here the size is area, because we're looking at surface. So stuff per unit size, and that's exactly what we mean by circulation density. It's, you might say, the thing that you multiply by area to get stuff. That's what density is. And so, again, we can throw out this idea and say, I'd like to know what is the associated circulation density, and the computations, details. I'm going to call it details that are very, very important to math, but that are, details that thankfully have already been worked out, that most engineers, I think, you don't need to worry about the details. But here is the punchline. The punchline, very, very important to understand, of course. Punchline is that this is that formula for density. It's curl dot orientation unit normal. Okay, so again, we've been down this road so many times, right? Accumulating quantity, boundary conventions, accumulation, viewing it as a stuff, interpreting a corresponding density. Here we are again. Okay. Is everybody all right so far? Okay. So, we put it all together. We have this idea of a quantity on little pieces of surface. Namely, you give me a little piece of surface, and we talk about the boundary circulation for that little piece of surface. That is a quantity. More to the point, it is wrong color. It is an accumulating quantity. The whole is the sum of the parts. You can do this boundary circulation on any piece of area. So if you take your surface and chop that surface up into a bunch of little pieces, that for the whole is the sum of that for the parts. So, boom, integral. Right? That's accumulation. And then there is the associated idea of density. Let's see here, color choices. Stuff is stuff per unit size times size. And arguably, depending on what kind of notations you prefer, we're done. Arguably, that's Stokes's curl theorem. But I do like the following rewrite. I think this is really nice. I think this is also mathematically important. And that is, in vector ds scalar, remember we have a nice little shorthand, little kind of catch-all notation to represent that, and that's the ds vector, which we talked about again a while ago and is very natural. So this is really a better way to write it down, in my opinion. So this is what I'm going to call Stokes's curl theorem right there. And just summarizing, boundary circulation is an integral of boundary circulation density. Or said differently, boundary line integral is a flux of the curl through the original surface. We doing okay? Everybody on board? Noticing the analogies, I hope and presume? Okay. A lot of people very reasonably call this Green's theorem in 3 dimensions. I mean, it's about boundary circulation around a 2-dimensional thing. Just like Green's theorem. It's just, this is how it looks a little bit different when that 2-dimensional thing isn't living in a 2-dimensional space. It's a 2-dimensional thing living in a 3-dimensional space. And so you have to account for things a little differently. Curl is computed by a different formula. Has some different algebraic characteristics. I mean, again, details and context. Aside from micro points, basically the same as Green's theorem. Okay. All right, and again, we have conditions. The vector field does have to be continuously differentiable, else problems. By the way, even at so much as a single point, crash and burn, serious problems. Well, it can kind of be finessed, but serious problems that we don't want to have to deal with, ideally. Okay, so don't lose sight of that. Okay, let's do one. As we've done with all of our boundary theorems, accumulation theorems, let's see here. Compute this line integral. So the question asks, and the vector field given and the curve given. Now, by the way, let me say a quick point about this example. This is a strategic point. So when it comes time to, taking a test, be it exam 3 or the final exam, whichever it might be, where you might see an example like this, it is tempting to look at this question, and it says, compute a line integral. We have various tools for computing a line integral. The curve is given to me parametrized. One of our tools that we have for how to compute a line integral works straight out of a parameterization. This appears to be teed up and perfectly, this is pointing right at pull back through the parameterization. That's, cosmetically, that's what this looks like, and don't buy it. Don't make the mistake of assuming that the way the question is phrased is going to point you toward what the best solution is. Life just isn't that way. Again, my past experience computing bazillions of these kinds of integrals is that, it just doesn't work that way. That the best answer is often, usually, to use a method that isn't exactly how the question seems to be, the presentation suggests, right? So please make a point of don't make cosmetic choices. Don't decide how you're going to solve a problem based on sort of what it looks like when it comes to you. That's a tragic error that would work out very poorly. Okay, so here's what we're going to do. We're going to look at our curve. Let's see here. The curve C is parameterized like so. So this formula for these values of t, thankfully, we recognize that formula. Right, we see cosines and sines. Okay, there's a minus in there, but that just points to a reflection. We know how to reflect things. Right? And so pretty quickly you'll recognize that that's just a reflected, unit circle in the xy plane. And you'll further recognize 0 to 2 pi means that you're going to go all the way around. So it doesn't take a whole lot of effort to persuade yourself that this curve, oriented as suggested by the parameterization, is that curve that I have in purple right there. Everybody okay with that? Okay, now we have our usual concern. Our usual concern here is, don't forget, if you're going to use this theorem, very importantly, this has to be a boundary. And again, this is not sort of, mathematician fussiness or anything. It's got to be a boundary. Otherwise, everything that led up to this theorem that critically depended on how exactly we define boundaries, which is what made the cancellation happen, which is what made it accumulate, which is what made everything work, right? Critically relies on it being a boundary. This is not fussiness. This is a necessary requirement to keep this from being utter garbage. Seriously meaningless garbage. And just for fun, I like to point out also that it has to be a boundary of something, because that something is your domain for your new flux. If your curve isn't a boundary of something, then there is no surface to even talk about flux through. So again, fall on your face, nonsense if it's not a boundary. So this is something to be very seriously worried about, and we got to address this question: is this curve a boundary? And I kind of regret having drawn this with the highlighter. Let me do this with the pen. It'll show up a little bit better. Yeah, that's better. Okay, so there's our curve. Is that a boundary? Now, again, don't make the standard mistake that students make in thinking about, as they should, thinking about orientations, is to oversimplify the orientation rule and think of it as like a clockwise, counterclockwise thing. And a lot of people would look at this and see, well, that looks clockwise to me, and that's not the rule, and so it looks like this is not a boundary. Well, I get it, right? But that is not clockwise. At least not, intrinsically. Because look at it from underneath. Imagine you get down real low underneath the XY plane and look at it from underneath, it would totally look counterclockwise. Right? So that's just not how boundaries work for surfaces in space. And in fact, this absolutely no problem is a boundary. This is a boundary of that surface, as long as we understand that we mean that surface in the sense of being oriented downward. Right? So that surface, oriented like that downward oriented disc. You play the game, human right hand, thumb in the direction of that downward chosen normal, orientation unit normal. And look which way my fingers swirl, right? They swirl exactly the way they're supposed to. How we do? Yes?
So it was just like a test question.
Yeah.
And we weren't given an image like that to look at. How would we know to use an oriented surface?
Yeah, by creating your own drawing, right? So this is, like much stuff in this course, this is an unavoidably intrinsically geometric collection of material. And so so the first thing you should do is draw the curve, and once you draw the curve and you see this picture of what this curve looks like, then you ask yourself, is that curve, can I think of some surface? And you just have to use your geometric intuition to think, that curve, that purple curve there is kind of the edge of this disc. And then all you have to do is think orientations and, which way does it go? And just, play the game. Yeah, is that satisfying? Okay. Anybody else? Great question. Yes.
How did you know that negative sign T means that it goes like...
Oh, yeah, right. So the one that we know sort of, more naturally, and I'm going to just kind of erase this little minus sign right there temporarily. But if I were to look at this curve, and let's look just at the x and the y, cosine, comma, sine. Well, that one we recognize, right? If I then think, okay, what about, adding the comma 0 at the end? That just says it's in 3 dimensions, but we're still in the xy plane, right? And so that curve right there, I know is like so. Right? Because again, it's kind of it was our very first parametric curve. And then, now let's come back and talk about the minus sign. When I put the minus sign in here, I notice that minus sign is exactly reflecting over this plane, over this line, or I guess you could say over this plane. Right, putting a minus sign on the y-coordinate literally just reflects through that plane. And so now I can ask geometrically, and I kind of regret my color choice there. Let me make this purple to indicate that's the reflection. And so once I realize that I'm just going to take that green curve and reflect it through this plane, then the resulting actual curve, that curve is just, it's literally just the reflection of the green curve, which you see is about like that. Is that cool? Yeah. Right. Okay, so we in fact do have a boundary suite. Let's see here. Let me remind myself. Okay, so this curve, that curve is a boundary. No orientation. Let's say it this way. We've already dealt with the orientation by choosing the correct normal vector for our surface. And with that noted, because it's a boundary of a specific surface, I can use Stokes' theorem and rewrite that circulation as a double integral of curl through the surface. That's where we pull out the big gun. We've now totally transformed the question from a question about a circulation into a question about a flux integral, right? And, totally different question. Fingers crossed, maybe this one works out better. Okay. All right, so let's see if it did. Now that we've got our our flux integral, there is the tedious matter that I do have to take my vector field and plug it in to compute the curl. Make sure you can do that. Now, we talked about the formula. We talked about the formula for curl back in chapter 3. Make sure you know that formula. You got to have that, good to go. Make sure you can compute it proficiently. That means reliably and quickly. Right? And make sure you can do that. Just glass smooth. And isn't this awesome? Look how much that simplified. The original vector field had a lot of ugly in it. The curl of the vector field, a constant, and even better, a constant that has some zeros all over the place. So that's a fabulous win. Naturally, I arranged it this way. Again, trying to make a sale here. I want y'all to be impressed with Stokes' theorem. So I arranged it to work out awesome. But that said, it actually works out awesome pretty regularly. This is not a narrow niche sort of a situation. This is not unusual. Okay, so there's our curl. The normal vector, again, we've already talked about. We had to choose the normal vector to be this, just to make the whole boundary rules work out. And, oh my gosh, look how nicely this dot product works out. The dot product is just -2. That -2 is a constant, and it's a constant being integrated over a garden variety geometric shape, right? Namely the unit disk. We totally know the area of the unit disk is 1 pi, right? And so, boom, we win. And our original integral that we were interested in, that line integral minus 2 pi. Everybody see how these work? Yes?
How would you have calculated the normal vector outside of the geometric interpretation?
Yeah, that's another great question. Again, I arranged it to be nice in this case, capitalizing on geometric good fortune that again happens surprisingly often. If it's not a surface that is just, super friendly like this, we parameterize. Once you parameterize the surface, you've got to go through take the partials, take the cross product. That'll give you your capital N vector. Then you got to worry about whether you parameterize the correct direction, just like in section 7.2. Yeah.
I'm just wondering because in 3D here,
yeah.
we only have one parameter.
Because what I gave you was a parametric curve. So yeah, so the curve parameterization was given, but then you, in a question like this, if you were to want to parameterize the resulting surface, you'd have to create your own parameterization for the surface. And by the way, that's why this is a great example of why I think I hate to be negative, but I think the book left out some really important stuff. They talk about how to interpret surface parameterizations. I spent time in class showing you how to create, such as one might need in a problem like this. Does that make sense? Okay. How we doing? Anybody else? Okay. All right. Moving along. Okay, so yeah, y'all may remember way back when we were talking about the fundamental theorem of line integrals, and we had written down the fundamental theorem of line integrals, and then I made this observation that, check it out, the TDS, we'll call that our dr vector, very natural, very convenient, geometrically natural, no less, which allows us to rewrite things like so. Right? And that allows us to reinterpret the idea of density. And this was a weird take. I know it was weird. Right? Well aware. Much more natural to think of a scalar notion of density. What you multiply by size to get, to get stuff. Right? It's stuff per unit size because it's what you multiply by size to get stuff. All scalars all the way. Old concept. And then I point out that, how are we going to make sense out of this? It's what we're multiplying by what am I going to think? The dr vector. How am I going to interpret this? And I propose this as being an oriented size. Right? And I call it an oriented size because of what's inside of it. There's an orientation vector inside of it, literally. And there's the scalar size inside of it, literally. Right? So I think oriented size just gets right up on it and labels it as what it really is TDS. So if that is an oriented size, doesn't it make sense to call this an oriented density? And I think that makes great sense. I'm a fan of this term. It again kind of speaks to exactly what that thing is. In an oriented sense, this is what you multiply, dot product to be fair, but what you multiply by size, oriented size to be fair, to get stuff. Then you change. Right? So, yeah, change being our stuff is why we call this an oriented change density. Okay. All right, so we're going to do a very similar thing down here for the context we're in now. Note how strong the analogy is. Again, previously, we had, initially we wrote down Stokes' theorem like this, and then we made the nice little observation that, hey, check it out, in ds, right? And now, this density, circulation density because it's what we multiply by size to get stuff, right? If I rewrite like I have below and ask how do I make sense out of this, notice, wrong colors. This, again, makes great sense as an again, think flexibly, an oriented size. Because again, look what's inside of it. Literally the orientation vector and literally the scalar size. Right? It's totally analogous to what we did when we were looking at the fundamental theorem of line integrals. So in the same way that we called dr oriented size, I'm likewise going to call this ds oriented size, and as such, this being what you multiply by oriented size to get stuff, I'm going to call this an oriented density. And of course the stuff in this case is circulation, so this is oriented circulation density. And I know it's a mouthful, right? It's a lot to digest. It takes some kind of getting used to. I urge you, dwell on the analogy. Dwell on how, what we're doing here is so similar to what we did here. Right? This is just kind of a rip-off of the little move that we pulled back then. And by the way, super important, because after all, curl is this important operator. I need to be able to make some sense out of curl. I need to have some sort of geometric intuition for what does curl look like. You don't want to make the mistake of thinking that curl is, it's a formula that you stick into an equation in this one place and then answers magically pop out. This is not. That's you don't want to make that mistake. That's viewing math as a magic trick, and it's really not a good way to truly learn math, right? So we're going to make sense out of curl now in a way that's totally analogous to how we previously made sense out of the gradient. So let's go back up here to the gradient. Here it is. Remember, the gradient I can break down into pieces. It has a magnitude and a direction. Let's see here. The magnitude, I already know. The magnitude of the gradient, think back. What's the geometric interpretation of the magnitude of the gradient? It tells you how steep the graph is. How much change per unit distance as you walk uphill. Directly, that is, as you walk directly uphill. And it also has a direction. The direction of the gradient, again, is uphill. Right? That unit vector direction literally tells you in which direction is the change actually happening. And then of course, look, if uphill is, let's say, straight that way, right? And here I stand on some hillside and uphill is that way and I could start marching uphill. I won't get the altitude gains if I go this way. Right? Now I'm just walking on a contour line. I'm not gaining any altitude at all. Uphill is that way. Right? So that tells you, in other words, that U vector tells you in which direction is that change actually happening. That's represented by that magnitude. Okay. Same thing happens with curl. Same thing. The magnitude tells you how much rotation is there in the fluid. By the way, kind of like Green's operator. Remember Green's operator to curl, two-dimensional curl. I like to call it Green's operator. Tells you how much of a rotation there is in the fluid. Same deal here. The magnitude of the gradient is telling you whatever the nature of the rotation is. We know we have a rotating fluid. Is it rotating, let's say, kind of like this? Or maybe it's rotating kind of like this? Or maybe it's rotating kind of like that. There's a bunch of different ways that it might be rotating, but the magnitude tells you how much. Is it a tornado level of rotation, or is it a just kind of a gentle, kind of a residual sort of little weirdness of just a micro rotation? Okay. All right. And the direction, just like you would expect, that U vector points in the direction of the axis around which the rotation is happening. Right? Now this is another geometric appeal I'm going to make. When something's rotating, right? However it might be rotating, that rotation should always be thought of as being around an axis. That u vector, the direction vector of the curl, that points in the direction of that axis. Okay. All right. So again, totally analogous. Same basic ideas. Geometrically different, of course, but same basic ideas. So let's make this. Let's draw some pictures. And by the way, what we have here, I'm just elaborating on what I wrote down here. The magnitude tells you, in some sense, how powerful the rotation is, and the direction tells you around what axis is that rotation happening. Everybody see what I'm talking about there, geometrically? The picture makes sense? Okay, let's talk through a couple scenarios. And I'm going to skip down real quick to some blank space, and we're going to talk first about gradient vectors. All right, so let's imagine first I have a gradient vector. Let's say my gradient vector points like that. Here's a gradient. All right. Well, if I go that way, am I walking uphill? Yeah. Right? It's steep in that direction. I'm going in the direction of the gradient. So yes, the magnitude of the gradient tells me that the mountain is steep. The fact that the direction of the gradient and the direction of my movement are in kind of the same direction, that tells us that I am experiencing that steepness. I am actually gaining altitude as I go in that orange direction. Okay. Whereas, on the other hand, same gradient vector. Suppose I go this way. All right. Well, now what's the story? How do I interpret this picture? Well, what this says is the fact that the gradient vector is long is what's telling me, yeah, the mountain's still steep, same mountain, but the fact that the direction that I'm going is not in that direction. I'm going orthogonal to that. I'm not exactly pretty close to orthogonal to uphill. That's what allows me to interpret, even though there is steepness, I'm not experiencing that steepness as I walk because I'm not walking in that direction. Right? Now, I hope that all makes sense. This is just this is flashbacks to chapter 2 and references to what it means to climb a hill versus to walk around a hill. Hopefully, that's not a challenging geometric observation. Well, here's the equivalent. All right, now think about these pictures while you're digesting what I have here. On the one hand, if I have a rotating fluid, let's say kind of like that, by the way, the rotation of which is represented by this curl vector. Right? And again, keep in mind the magnitude tells you how much the fluid is rotating. The direction of the curl tells you around what axis. Okay. Well, let's see here. Let me point out by the way, same thing here. Same fluid. If I am walking, let's see here. You know what? I don't like that just turned into a mess. If I am looking at a piece of surface where the orientation on the boundary rotates around the same way that the fluid is rotating, clearly I'm going to get a lot of circulation. I'm going to experience as I go around this curve, I'm going to experience a lot of circulation because the fluid's going the same direction that the curve's going. Sure, right? But we can notice that by the fact that curl and the normal vector are pointing in the same direction. right? So that green dot product, curl dot n, right, is an algebraically convenient way of representing that, my boundary that I'm looking at is going around in the same direction that the fluid is going around, right? So those vectors pointing in the same direction is geometrically simultaneous with those rotations going in the same direction. And, on the contrary, let's see here, if I were to look at this scenario where, okay, now there's same rotation of the same fluid, if I were rotating around in a totally different direction. Right? Totally different. Yeah, there's a lot of rotation of fluid, but I'm just not, my boundary is not rotating around the same way. You're not going to experience any circulation there. Basically no circulation. You're not going around the same direction the fluid is, and that's going to be detected by the curl and the normal vector not pointing in the same direction. Right? So in some sense, failure to get circulation happens because of failure of those green vectors to point the same way. So it's just like here. Either way, there's steepness. The question is, how much of that steepness do you experience? Either way, there is a rotation of fluid. The question is just how much of that rotation are you picking up on the boundary of your actual little piece of surface? So, very strong analogy there. I hope you'll spend a little time, again, thinking about the algebraic comparison here between fundamental theorem of line integrals and how we develop Stokes' theorem, how we interpret the integrands as oriented densities, and how geometrically they're different, but kind of analogous. Okay. All right, let's see here. We'll do a little bit on the physical examples. This first one's pretty straightforward. Thinking back in the plane, curl is, Green's operator. It's a scalar, and curl just as a way of representing how much the fluid has a rotational aspect to it. And while the vector field might represent velocity, and that's going to tell you how the fluid is moving, and therefore how the leaf is moving, curl is going to tell you how the leaf is rotating. Right? Totally different thing. And super convenient that curl is this very simple little formula. It just gets right up on it and tells us exactly what is the nature of the rotation in that fluid. Again, one of my favorite examples of a rotating fluid where none of the flow lines curve, right? Those flow lines are all straight lines. But, how's that leaf going to rotate? Well, it's being pushed harder on one side than the other. It's going to rotate to how I have it drawn there. Right? So, same thing in 3 dimensions. Really, really similar. Very, very similar. Now, though, the rotation represented by curl is just a little bit more complicated. The rotation represented by curl, I have to describe around what axis is the air, water, whatever, the fluid rotating. And then, once I've established around which axis, I can talk about how strong is the rotation around that axis, right? And in the same way that this curl tells me how the leaf rotates, likewise in 3 dimensions, if you had some floating balloon, something analogous that just goes exactly where the fluid tells it to go. And so I think a floating balloon, 3 days after the party, when it's not up on the ceiling anymore, it's just got that perfect buoyancy. You don't want to wait 5 days. In 5 days it's on the ground. But like 3 days after the party, it's just perfectly balanced and just floating around in the air. Such a floating balloon, curl tells us how that balloon is going to rotate. Does that make sense? Everybody buying it? Everybody see the analogy, how it's the same idea, just appropriate to 3 dimensions. Okay. All right. right. Let's see. Oh, we're out of time. Okay, so we will draw the line right here. And y'all have a great weekend. See you later.